Hi everyone, this is Mr. Chu over here. Today I will move on to a new topic, which is topic 9.2, that is on single slit diffraction pattern. Now let's start off with something that you have seen before and something that you may know. In fact, you should know. So the thing is, for topic 4.4, we have gone through the phenomena of diffraction. And the phenomena of diffraction is that if you've got a wave passing through this slit over here, you will have this wave coming out like this, and if you were to tighten up the hole size, you will find that the wave starts to do this, and when you close it up enough, you will find the wave doing this. So what is the difference? The difference is, drum roll, it is the size of the opening relative to the wavelength. So if the wavelength is very small compared to the hole size, then you have almost no spreading at all over here. And if you were to have a hole size that's comparable to the size of the wavelength, that's when some spreading happens. And when the hole size is equivalent to the wavelength, or even smaller, if the hole size is even smaller than wavelength, then you have a full spread from 90 degrees to 90 degrees, 180 degrees. So the hole size relative to the wavelength is a key to the amount of spreading that you have. The question is why? Why is it so? Why do we have to accept this? Is there a more fundamental reason? Yes, and I'm going to go through two levels of derivation and show you why this is so. But I must make it clear that any derivation I'm going to show you, it's going to be not in syllabus. It is good to know. And the two levels of the derivation, one is the simpler one, and there are flaws that I'll go through with you. So look out for the flaws as you listen to my derivation. And there will be a much more elaborate one, which is the full derivation that will get you the graph of the intensity versus angle kind of graph. So let's begin with the simpler one. Let me emphasize again, any derivation is not in your syllabus for this section. So let's just take a look at this. Now if I got a hole size which is D, I cut it up into two smaller slits, and therefore the separation between the two of them will be D upon 2. And if they were to have a ray at a certain angle, please remember that this is not saying that the wave only goes in this direction. The wave goes in all directions, just that it happens to, we will just take one arbitrary angle theta. Okay, just one random angle theta. Now the extra distance that this wave travels is this one. Now let me magnify this, clean this up a little bit. So this is the source, this is the source, this is D upon 2. So the additional distance is here. If this is theta, this is 90 minus theta, this is theta. Therefore, D upon 2 divided by, rather path difference divided by D upon 2 is equals to sine theta. So path difference is equals to D upon 2 sine theta. And if you want to find the first minima, I'll explain later why the first minima, you'll find that sine theta is equals to lambda upon D. So what's the significance of the first minima? First minima means that that's the point where the intensity first goes to 0. At this point, in this direction, it is very strong signal, and first minima is the first position where it goes to 0, which is this position. That's the position where it goes very weak. So that's why we're interested in the first minima. And if we take a look where the case where lambda is very much smaller than the D, then theta is approximately 0. Now what does this mean? It means that there is no spreading. The first minima occurs at a position directly opposite the opening. So that's no spreading in physical sense. If lambda is just slightly bigger than D, then we have a non-zero solution where sine theta is just lambda upon D. Now when we have lambda equals to D, this is interesting, sine theta equals to 1, theta equals to 90 degrees. So what we have over here is a case where the wave spreads at 90 degrees to the original direction. So therefore the wave spreads to end over here. And that's how we can understand mathematically why these three scenarios are the way they are. However, there's a big flaw over here. Oh yes, before I go on to the flaw, what you need to know about this is that if I got a light ray or sound wave going through, you need to know that intensity versus theta will look like this. There are two things I'll look out for as an examiner. Where sine theta is equals to lambda upon D, this is sine theta equals to lambda upon D. So the first point is the position, you need to know the expression for it. Second point, the general profile of this, such that this is about 9 to 10 times bigger than this. So you need to make sure that it is the size of the opening is the size of the intensity is approximately 9 to 10 times this compared to this. Now there is a floor. And what's the floor? I'll give you 5 seconds to try to think about the floor. Now the floor in this derivation is that why 2 slates? Why not 3, 4, 5, 6, 7, 8, 9, 10? So the thing is that this derivation only works for 2. It doesn't work for 3. If I cut it into 3, it no longer works. If I cut it into 4, it also doesn't work. In fact, it also doesn't predict the correct positions of the maximus and the other minimus. So what's the full derivation? Now this is the part where I will go into the full derivation of the wave over here, of the pattern over here. Now this requires 2 fundamental ideas, the complex representation of wave and also the complex representation of wave and also GP, a geometric progression. I'll show you why. So let's take a look at this. Instead of cutting into 2 slits, we cut it into n slits. So let's consider these 2 sources over here. They produce wave over there, and if I magnify this portion, if this size over here is d, because I cut it into n number of slits, the separation between them will be d upon n. And if this is theta, the same method, the path difference will be d upon n sine theta. Reference to the previous, just a couple of minutes ago, the way that I derived the path difference. And this phase difference then is 2 pi upon lambda d upon n sine theta. So if you are not very clear about sine theta, phase difference, refer to the video that I have earlier regarding phase difference. Alright, now the way we denote the wave is for the first source over here, this is the first source, let's denote it by this. And the second one is going to be x naught ei omega t plus phi, and then x3 is x naught ei omega plus 2 phi, and then xn is x naught e I omega t plus n minus 1 phi. So if we add them up together, what do we have? We're going to have this expression, x equals to x naught ei omega t plus x naught ei omega t plus phi plus x naught ei omega t plus 2 phi plus x naught ei omega t plus n minus 1 phi. I bring this up over here. This is equals to x naught ei omega t 1 plus ei phi plus ei n minus 1 phi. As you'll see over here, this is actually a geometric progression with A1 and the R as ei phi. So if I were to apply the geometric progression formula, the sum to n terms, it will look like this, and this is x naught ei omega t. This is just simply 1 I n phi divided by 1 minus ei phi. And this is where I play a little bit of math magic. Ei omega t, ei n upon 2 phi, ei phi upon 2. I factorize these 2 out from here, and this is going to be minus n phi upon 2 minus ei n phi upon 2 divided by minus I phi upon 2 minus ei phi upon 2. If you remember your complex number, this is actually sine of the number over here, sine of the number over here. And I will combine this whole thing into 1 minus 1 upon 2 phi, and this will be sine n upon 2 phi divided by sine phi upon 2. And I will leave this here, this whole thing over here, it's the same. Let's focus on this portion. So this will be sine n upon 2. Phi itself, if you refer to that thing over there, is 2 pi upon lambda d sine theta. Alright, and it's upon n. Forgot about upon n. And then this is sine 2 pi lambda d upon n sine theta times half. So let's do some cancellation and cancellation. So this is again equals to this, and this is sine pi d sine theta upon lambda divided by, now this is divided by n. Now if we were to push n to infinity, very big number, because by right it should be very close to each other. Now this is going to be small, and when this is small, sine theta is approximately theta, so that's why I can remove the theta. And upon n over here, I can bring this up, and this whole thing times n. So this is the time independent, there's no time over here, can you see that? Whereas this has time over here, omega t. So this is the oscillating bit, this is the amplitude. And if you just square this portion and plot this squared portion against theta, you're going to get this very beautiful wave pattern that looks like this. And where lambda upon d sine theta equals to lambda upon d sides. Let's do a check. If sine theta equals to lambda upon d, if we plot sine theta equals to lambda upon d over here, lambda, numerator, denominator cancel, d cancel, so this term becomes sine pi, which is 0. Therefore, this whole thing goes to 0. So it matches what we predict. So this is the method, and this is the derivation for the single slit diffraction pattern. Totally not in syllabus, but it's always good for you to know how you get that wave pattern over there, rather than just now the game. And I believe you learned complex number in GP before, so it's not totally new. Alright, let me repeat again what is in syllabus. You must be very clear about that so that you don't get confused about what's the core and what's the bonus. You must know this graph over here. You must know how to sketch the graph. You must know the position of the first minimum. Just a reminder about the first point. What do I mean by knowing the graph? You must be able to draw the graph and such that this and this maxima, first central maxima and first maxima after the central maxima, is about 9 to 10 times difference. Alright, and that's all I have for you, so hopefully you have better graphs of single slit diffraction. I'll go to 9.4, which is resolution. It builds on this topic, and then I come back to 9.3 later. Thank you.